So we're going to quickly go through the answers to the probability application task from RLT3. I think these will be really beneficial for the CAT, as the sort of problem solving and the mathematics you're doing is quite similar. So question 1A, you have a regular deck of cards, which in a regular deck of cards there are 52 cards. Obviously, there are 4 aces, and there's 42 other cards that aren't aces. In a game of poker, the dealer gives you 5 cards. We want to know how many combinations exist where you get exactly 4 aces and 1 other card. So what's happening here is, say you've got 4 aces and 1 other card, could be any other card in the deck. You're doing, sort of like you're focusing on 2 different groups here. You've got cards that are aces and cards that are not aces. So those are your sort of 2 groups. And what you want to do is you want to select 4 aces out of 4 possible aces. So we're selecting all 4 of the aces, and there's only 4 aces in a deck. Now, as for the cards that are not aces, we are only selecting 1 non-ace, we'll call it a non-ace, out of 48 non-aces. Maybe so we don't get confused, I'll call them others. That's really breaking down the problem here. That's what we're doing. We are selecting 4 aces out of a possible 4 aces, and then we are selecting 1 card out of 48 other cards. Now, what does this look like as in mathematical terms? Well, if you isolate the problems, if you are asked to select 4 aces out of a possible 4 aces, what you're doing is you've got 4 aces and you want to find the number of combinations when you're selecting 4 of them. So it's 4C4. Now, when you're selecting 1 card out of 48 cards, similar thing, you've got 48 cards to choose from and you're selecting 1. So let's see, what is 4C4? Put that in our calculator. If we remember the formula, it should be 4 factorial over 4 factorial times 4 minus 4 factorial. That gives us 1. And 48C1 will give us 48 factorial all over 1 factorial times 48 minus 1 factorial. And that gives us 48. Now, what do we actually do with these numbers now that we know? Well, you can think of the question as what you're doing is you're selecting 4 aces out of 4 aces, and you need to select 1 other card. So remember that often when we have the word and, it means we're using the multiplication rule. So we're doing 2 separate, you've got 2 separate groups that you're choosing from, which means you need to multiply them. So what we're doing is the number of combinations in total is 1 times 48, which is 48. There's 48 different combinations exist where you can choose 4 aces and 1 other card. Now we want to look at what's the probability of this happening. We've got the number of combinations that are possible. Now what's the probability? What we need to remember is what's the formula for probability? The probability is you get the number of ways an event can happen and you divide it by the total possibilities. I think I spelled that right. Enough for now. So the probability is the number of ways an event can happen divided by the total possibilities. In this case, our event, number of ways our event is getting exactly 4 kings and 1 other card. We should notice that this is it's a symmetrical problem to what we've just done. Doesn't matter if it's 4 aces, 4 kings, 4 jacks, 4 fives. As long as it's 4 cards of the same type and one other card, it's going to be the same. So the number of ways we can select exactly 4 kings and one other is 48. Because we've just done that. That's the number of ways our event can happen. Now all we need to know are the total possibilities. We might be asking total possibilities of what? What are we talking about? If we look at the problem, what we're actually doing here is we are selecting 5 cards, so 4 kings, one other card, but we're selecting 5 cards out of a deck of 52. So the total possibilities, or maybe total combinations, for selecting 5 cards out of a deck of 52. So if we're selecting 5 items out of a total of 52 objects, that's going to be 5C52. 52 factorial over 5 factorial times 52 minus 5 factorial. That's a large number. That's how many combinations there are. So 2,598,960. So now that we've got our number of ways the event can happen and our total possibilities, we just want to chuck it into this fraction. Now maybe that simplifies to something. We'll have a look. It does. Did I type that incorrectly? That was just luck that I guess luck that this number was actually a factor of 45. That's interesting. So that is our probability of getting exactly 4 kings on one of the cards. Question C asks, what is the probability of getting exactly 4 aces or exactly 4 kings? So again, we're looking at probability. So the number of ways the event can happen divided by the total possibilities. Now, because again, this should be stated actually, getting exactly 4 aces and one other card. That wasn't mentioned, but more implied, or exactly 4 kings and one other card. So we're still looking at selecting 5 cards in total. So the total possibilities is going to remain this number. The total possibilities for selecting 5 cards out of a deck of 52 is going to stay the same. The only thing that's changing is the number of ways the event can happen. And that's because the event has changed. We're looking at getting exactly 4 aces on one other card, or exactly 4 kings on one other card. That or is the key word here. Remember that often when we have the word or, it refers to the addition rule. So the number of ways we can get 4 aces on one other card, we already worked out that there are 48 ways that can happen. There are also 48 ways you can get 4 kings on one other card. So we're just adding those combinations together, which gives you 96 combinations in total. So in this case, the probability will then be 96 over this number. and that will simplify to 2 over that denominator. So that's the probability there. Part 2. So in a regular deck of cards, there are 13 different sets of cards. So what I mean by a set is you can have aces, 2s, 3s, 4s, 5s, so on, all the way up until Jack, King, and Queen. The number of combinations that exist when you're choosing one of these sets is therefore 13C1. So what I'm saying is if you had to choose one of these sets, you have 13 sets to choose from, and you're choosing one of them. So it's 13C1. So it's 13 different ways you can choose one of these sets. Using your answers to part 1, that's a mistake, sorry. Be the number of combinations, that's probably better. The number of combinations of getting a 4 of any kind of set would then be 13C1 multiplied by our answer to part 1. So using that information, we want to find the probability of getting a 4 of a kind in any set. So from aces, 2s, 3s, 4s, etc. What are we actually talking about here? We've got one example is 4 aces and one other card. That's one option. Another option is 4 2s and one other card. Another option is 4 3s, one other card, and so on. So you can understand that if I kept going all the way down to kings, there would be 13 different options here in total. Now that 13 is equivalent to 13C1. So what's going on here is you could just assume that it's 13 multiplied by 48 different options every time you choose a different set. Another way to think of it is you're choosing a set, one set out of 13, and then you're choosing 4 out of 4 of those cards, and one other card. That's what we're doing here. So if we're choosing one set out of 13, that's your 13C1. Then we're choosing 4 cards out of 4. Say, for example, if we did choose aces, we're choosing 4 aces out of 4 aces. And then finally, we're choosing one card out of a total of 48 others. So that's the number of combinations where we can get a 4 of a kind in any set. That's what is 13C1? It's 13 factorial over 1 factorial times 13 minus 1 factorial, which is 13. This is 13 times, we already know 4C4 was 1, we did that earlier, and 48C1 is 48. So that is just 13 times 48. 624. There are 624 combinations where you can get a 4 of a kind in any set. That's the number of ways this event can happen. We already know the total possibilities is the 2,598,960. Therefore, the probability is the number of ways that event can happen, 624, over the total possibilities, which gives us 1 over 4,165. That is the probability of getting a 4 of a kind in any set. This is where things get a little bit more tricky. A full house is when you have 3 cards of the same set and 2 cards from another set. So for example, you could have 3 queens and 2 jacks, as shown here. We want to find the probability of getting exactly 3 queens and 3 jacks. So we're going to start off with that. So what we're doing is, to get exactly 3 queens and 2 jacks, what we're doing is we are selecting 3 out of 4 possible queens, and then we are selecting 2 out of 4 possible jacks. So as combinations, what this looks like is we've got 4 queens and we're choosing 3 of them. And, because it's and, so we multiply, and we're choosing 2 jacks out of a possible 4 jacks. So this looks slightly more complicated than what we're doing before, but it's essentially the same logic and the same calculation. In these examples here, we were choosing 4 aces and 1 card that was any other card. So we had 4 aces. We're choosing 4 aces out of 4 possible aces. And then we were choosing 1 card out of 48 others. So exact same thing here. We're choosing 3 queens out of 4, and we're choosing 2 jacks out of 4. So we just need to work out what these are. So 4C3, 4 factorial over 3 factorial times 4 minus 3 factorial. That's 4. Now 4C2, I'm just going to change these numbers to 2. That's 6. 4 times 6 is 24. So there's 24 different combinations that exist where we can get this exact arrangement of a full house. Now again, probability is the number of ways the event can happen divided by the total possibilities. Again, because we're selecting 5 cards out of 52, the total possibilities isn't changing. Therefore, the probability is just 24 over our total possibilities. And that simplifies to this number here. We've got 1 over 108,290. That's our probability of getting this exact arrangement of a full house. All right, question C. How many combinations of different sets are possible in a full house? So what I mean by this is you could have 3 2s and 2 3s, or maybe these are, you have 3 9s and 2 aces. So any combination of 2 sets. So this one is the trickiest one we've done so far. So how many combinations there are. So what we're doing is, first thing we're choosing is, we're choosing 2 different sets out of 13. So we could have, say, queens and jacks, or you could have in this case, actually, order is important because 3 queens and then 2 jacks is actually not the same as 3 jacks and 2 queens. So we're actually going to use permutations for this one, but we'll get to that in a moment. So we're choosing 2 different sets for our full house out of a possible 13 sets. And then what we're doing is we're choosing 3 out of 4 for one of the sets, just like we had 3 out of 4 possible queens. And then we're choosing 2 out of 4 for the second set, just like we chose 2 out of 4 jacks. So let's do this in terms of our permutations and combinations. So choosing 2 sets out of 13, in this case, the order in which we choose them does matter. So we're going to use permutations. We've got 13 sets to choose from. How many ways can we arrange 2 of them from 13? Then we are choosing 3 out of a possible 4 queens. I mean, not queens, sorry, any set. Queens was from the previous example. And then we're choosing 2 out of a possible 4 for our second set. So what is this equal to? Work out 13p2. So we've got 13 factorial all over 13 minus 2 factorial. That's 156. Now, 4c3 was 4, and 4c2 was 6. So we've got 156 times 4 times 6. So 3,744. That's how many combinations of different full houses you can have. And again, because we're choosing 5 cards, our total possibilities remains the same. So the probability is just going to be 3,744 ways that we can get a full house divided by the total possibilities for choosing 5 cards. That is 6 over 4,165. Question D. Using your answers to part 2B and 2C, calculate the probability of getting a full house with any 2 sets. Oh, I think I've sort of skipped ahead here. I've already done that. I've worked ahead of what I needed to do. All right, so that is how you complete the probability application task. As I said, part 2, so this, all the calculations and all the sort of the mathematical logic we used in part 2 for the full houses will come in handy for the CAT.